In this section of the math module, we're going to look at significant digits. So up here, I have two different balances. This here is called an analytical balance. This here is called a top loader. The top loader is something you would see in early chemistry classes. It costs about $120. The other balance costs around $4,000. Why the difference? This only reads out to 2 decimal places. This reads out to 4. That reading is so significant that if you take a piece of filter paper, you can actually weigh your thumbprint. So the difference here is due to the precision of measurement. Now, precision of measurement when it comes to chemistry, we often see it represented as significant digits. So let's talk about rules for counting significant digits and writing significant digits. First, when listed, all non-zeros are significant. You'll see me write significant as sig. So when I look at 100, only the 1 with what we said so far is a significant digit. Trailing zeros are non-significant when no decimal is present. So when I look at 100, these zeros are trailing zeros. They are not significant. So with 100 with no decimal point, there is only 1 sig fig, which I'll be writing as SF. Next rule. Trapped zeros are significant. So when I look at 101, this is a significant digit. This is a significant digit. That 0 is significant. Therefore, there are 3 sig figs in this particular one. Next rule, leading zeros are not significant. You can kind of think of this in terms of scientific notation, and it's one of the reasons why scientific notation is used so much is because it allows us to easily track sig figs. When I look at a scientifically notated number up here at the top right-hand corner, all of these digits are significant. This is essentially just telling us the scale. It's the same thing with trailing and leading zeros. Down here in the lower left-hand corner, this 0.011 has 2 zeros in front. These are leading zeros. They're not significant, but these 2 ones at the end are. Therefore, there are 2 sig figs here. Trailing zeros, when a decimal is present, are significant. This decimal is important. So when I look at this 100 here with this decimal, this actually has 3 sig figs. When I look down here at this big number, this is a trapped 0, it's significant. This is a trapped 0, it's significant. And this is a trailing 0, but the way we can tell that it is significant is because we have a decimal place, or a decimal point here. So I have 1, 2, 3, 4, 5, 6, 7 sig figs with this number. So why do we care about significant digits? Well, we can use the example up here at the top as kind of to put things into perspective. A graduated cylinder is a fairly precise instrument. So we can usually get out to the first decimal place and sometimes the second decimal place, depending on how precise the instrument is. And this will be in milliliters. Okay, so there are 1,000 milliliters in 1 liter. Now the swimming pool over here, an Olympic-sized swimming pool has 2,500,000 , 000 liters of water in it. This is the last significant digit. So if I were to add a milliliter water from the graduated cylinder in the swimming pool, we would see no difference in between the starting volume and the ending volume. Think about if you have money, okay? If you only have $10 to your name and you gain or lose $1, that's a pretty significant difference. But if you're a billionaire and you gain or lose $1, it's not going to make that big of a difference to your ending amount. Now, in the sciences, we have a way to work through this determination if these numbers are significant or not, and whether or not they have an impact on our final answer. So we have rules whenever we're doing mathematical operations. The first is when you add or subtract, use the least precise number as a guide. So we can think of the least precise number as being the one that is reported to the least number of digits to the right. So if I have something like this and this is my least precise number. You need to be careful whenever you're getting answers out of a calculator because the calculator doesn't know how to do significant digits. So for example, if I take 45.217 and I add it to 6.3, the bottom number has the least number of precise digits. It only goes to the tens place. When I punch this into the calculator, I get out 51.517. My final reported answer, though, should only be 51.5. Notice that it doesn't matter how many digits this bottom number had on the left-hand side. All that matters is the number on the right. For multiplication and division, we need to count the number of sig figs. So our final answer uses the least number of sig figs determined from those that went into the operation. So for example, if I take x.xx and I multiply it by xxxxx, this has 4 sig figs, this has 2 sig figs. My final answer will have 2 sig figs. Again, you have to be careful whenever you're punching this into the calculator because if you're not careful, you'll report more digits than you should. So if I take 21.93 and I multiply it by 43.0, this has 4 sig figs, this has 3 sig figs. I should report it to 3 sig figs. My calculator gives me 942.99. So my final answer will be 943. When you have multiple operations going, though, you need to keep track of your sig figs as you go along. It's very important not to round until the end. That causes what are called rounding errors. So in this problem, I have 2 different operations going on. I have my additions going on, and then I have my divisions going on. So what I'm going to have to do is keep track of each part of the problem as I go along. When you are confronted with a problem like this, where it's difficult to tell who's the least precise number, or you're not sure, you should write out these numbers as decimals. So for example, 8.60 times 10 to the negative 1 is 0.860 plus 423 divided by 0.0129 plus 0.0994. Now notice that this 0.860 is not going to have that much of an impact. In fact, when we add these numbers together, the last place I'm going to report is my ones place. But we do not round to the end. So if I were to write this down into my next step, I would write the top as 423.86. And what I do as I go along is I underline the last significant digit. Sometimes it's important to note that you're going to have a lot of digits. To get the best answer, I recommend that you just keep everything in your calculator. But if you have to write a number down and you don't want to repeatedly write all of the numbers that come after a decimal. You need to keep at least the digit after the last significand. So that would be this 8 right here. So then I do the bottom part here, which ends up giving me 0.1123. 3 is the last significant digit. So now I'm going to divide these two, and I have 3 sig figs up top, 4 at the bottom. So when I write down my final answer, I should write it as 3 significant digits. So I could do it like this, or I could write it as scientific notation, which would be 3.77 times 10 to the third. Notice that with scientific notation, all of those numbers are significant. This 0 here is not significant for our final answer. Now we're going to look at significant digits for logarithms. So log rules can be thought of very similarly to scientific notation rules. Notice that the number in a scientific notation, right, is all significant, but that times 10 power has nothing to do with it. So a logarithmic scale means that each time you go up by a digit, you're increasing by a specific factor. With just regular log, it's called base 10, meaning that every time you go up by a number, you're going up by a factor of 10. So there are two components of a logarithmic answer. Okay? In other words, a number that has had the log taken of it. When I look at this and I punch it into my calculator, I get a number, and it's negative 0.670805, so on and so forth. So if I were to look at this number, before I take the logarithm out of it, I have 4 sig figs. For a log, we can think of the number that's before the decimal point as being what's called the characteristic. This is like that times 10 power. It has nothing to do with the number. All of these digits over to the right, on the other hand, are called the mantissa. The mantissa is where we have the number of sig figs. So all of the numbers that we report in a mantissa are significant. The characteristic has nothing to do except for as a placeholder to tell you what values we have. So if I were going to report this out properly, I would have negative 0.6708 as my final answer with 4 sig figs here. The final thing that we're going to go over for this particular section is rounding rules. So most of you should be familiar with, if you're greater than 5, you round up. If you're less than 5, you round down. When we're talking about that, what we're talking about is the last significant digit. So if I have 345.6 and the 5 is my last significant digit, this 6 is greater than 5, so we round up. So this number becomes 346. So when you're greater than 5, round up. When you're less than 5, you round down. And again, this is the number that is just past the last significant digit. So again, if I have 345, this time I have 4 here. 5 is my last significant digit. I would round down, and this becomes 345. Now, what happens if it's equal to 5? Well, in many classes, you're just told to round it up. The better rule for this is called rounding even. So in other words, you round that last significant number to an even number. So if I have 345.5, I have two options. I could either round down to 345, or I could round up to 346. That would make the 6 even and the 5 odd. In this case, we round even. We go to 346 as our final answer.